Hi everybody, welcome back to Algebra 2. Today we're going to take a look at Chapter 5, and we're going to start things off with 5.1 Quadratic Functions. Some new vocabulary we're going to take a look at today. Quadratic functions, quadratic terms, linear terms, constant terms, maximum value, and minimum value. So today we're going to focus on the graphing of quadratic functions, and eventually we'll get into what they're used for, how they can be applied in real-world situations, and things like that. But I figured to start things off by showing you a few examples of what these actually look like. So when we graph a quadratic function, we're going to get a shape that looks similar to this. That's actually what's called a parabola. Let me write that word out for you here. P-A-R-A-B-O-L-A, parabola. So basically, everything that we're going to be graphing here today should have this general shape one way or another. Now these are all opening down. We're also going to take a look at some parabolas that open up. But you can see anytime gravity is involved in a free fall object, you're going to get that given shape. So here's some basketballs bouncing, you got the water fountains flowing. They're also used a lot in architecture. So here's the Gateway Arch in St. Louis. We have a roller coaster. We have a bridge. We have a temple of some sort, and then we have an archway. So you do see these objects in quite a few different places around the world. All right, so let's start things off here. Here's the graph of our quadratic function. So this is the general idea of what it looks like. The equation for our quadratic equation is going to be y equals ax squared plus bx plus c, where a does not equal 0. So basically, a quadratic function is anything that has an x to the second power. Some few things that we're going to be looking for when we graph these. First off is going to be the y-intercept. The y-intercept happens whenever x is equal to 0. So you can see I just simply took my equation here, ax squared plus bx plus c, and we're going to let x equal 0 in this case. And if we let x equal 0, this whole term and this whole term both go to 0, which means the only thing I'm left with is c. That's the y-intercept. That's the spot where the graph will cross the y-axis. Next we have the equation of the axis of symmetry. The axis of symmetry, every parabola you draw is going to be symmetrical, meaning I can take this graph, I can fold it in half, and the right side's going to lie on top of the left side. And that's going to happen for every single parabola that you draw. This equation right here, the equation of this line, can be found by doing negative b divided by 2a. Keep in mind, b is this term here. It's the term in front of the x, or the term in, the coefficient that's in front of the linear term. The a is the coefficient here that's in front of the x squared term. So this would be your quadratic coefficient. This would be a linear coefficient. This is simply the constant. Axis of symmetry, and this red line, negative b divided by 2a, and that is the x-coordinate of the vertex. So this value that you get out, not only is it the axis of symmetry, but it's the x-coordinate of that vertex of your parabola. Now, what's nice about these is that when you graph, you're going to be plugging in points, but you only have to do half the work, because if you're able to find one point on the side of an axis of symmetry, well, then you could just flip it over, reflect it over that red line, and bam, there's a second point. So you're going to be graphing the whole thing, but you're going to be doing about half the work of what you normally do. Alright, so let's take a look at our few steps here for what needs to be done in order to graph quadratic functions. So step 1, we're going to find the coordinates of the vertex. And again, remember, to find the coordinates of the vertex, we're going to take the negative b divided by 2a. After you find that vertex, you're going to create an input-output table, or simply an xy chart. You can then select several other values of x and substitute these values for x into the equation and solve for y. Again, that's just going along with your xy chart. And finally, plot each of the ordered pairs on the plane and draw your parabola. These parabolas are going to go one of two ways. So it's either going to be a parabola that goes up, or it's a parabola that goes down. You're not going to deal with sideways parabolas quite yet, because in that situation, it's not going to be a function. We're only dealing with quadratic functions in this chapter. All right, so let's give one a try here. Consider the quadratic function 2 minus 4x plus x squared. First thing I want to do is I want to find the y-intercept, and we'll try to color code this as best as possible. So starting with the y-intercept here, y-intercept is going to occur whenever x is 0. So I'm going to start off my xy chart. I'm going to take 0, and I'm simply going to plug that in for x. And if I do that, I'm going to get 2 minus 4 times 0, which is 0, plus 0 squared, which is 0 again, which means that's a y-coordinate of 2. So the point 0, 2 is a point on my graph, and it's the y-intercept. Next, let's go ahead and find the axis of symmetry. Axis of symmetry, I'm going to abbreviate AOS, axis of symmetry. And the axis of symmetry is x equals negative b over 2a. In this case, b is the term that is with the linear value, so it's going to be your negative 4. So we're going negative negative 4, which is going to give me a positive 4, divided by 2 times a being the term that's in front of the x squared, so 2 times 1, which is 2, gives me a value of 2. So my axis of symmetry is at x equals 2. And what I do is I find x equals 2, and you draw a dotted line. Now, axis symmetry is at 2. I need the whole point. I need the y-coordinate that goes along with it. So let's take 2, let's plug it in, we'll see what we get. So this is 2 minus 4 times 2, which is going to give me 8, plus 2 squared, which is going to give me 4, for a total of, looks like, negative 2. So the point 2, negative 2 is on my graph, and what makes that special is that is the vertex. Coordinates of the vertex, right there, 2, negative 2. I'll make that blue so we can differentiate here. Finally, we want to use this information to graph the function. Unfortunately, this isn't quite enough for me to graph, so what I'm going to do is I'm going to get one additional point here. I usually recommend one more just to make sure you're good. So I have 0, I have 2, let's try 1. We'll go in between there, and you can pick any point you want. Don't get too far away from the vertex. These grow pretty fast, so the further away from the vertex you are, the larger your problem is going to be, and it's going to be tough to fit this on the graph. So if I plug in 1, we'll have 2 minus 4 plus 1, which is going to give me a value of negative 1. Which I can plot right there. Now, here's the beauty of the parabola and the axis of symmetry. Now that I have these points, all I need to do is take them and flip them over to the other side. And when I flip them over, following the rules of symmetry, I end up with the other half of the parabola. And now it's just a matter of connecting our points together. And voila, there's our graph. Next thing we want to talk about here in your parabola is every parabola, I said before, is only going to open one of two ways. It's either going to open up or it's going to open down. The way it opens depends on the value of A. This will open up and has a minimum if A is greater than 0, meaning if A is positive. So if A is positive, you got a parabola that's going to open up, which means you're going to be having a minimum value. If A is negative, well then the parabola is going to open down, and that vertex point, that's going to become the maximum. So let's give it a try. Consider the function negative x squared plus 2x plus 3. Determine whether the function has a max or a min. So let's start there. The very first thing I do is I figure out what A is. And A in this case is negative 1. And since A is negative 1, it means the parabola is going to open down. And if the parabola is opening down, it means this point right here, that vertex, has to be a maximum. So I know I'm going to get a maximum value. So next question says, well, what is this value? That value of the max is the y value of that vertex. So I'm going to go through my steps that I normally did, just like with the last problem, to find my vertex. And remember, the x-coordinate of the vertex is at negative b divided by 2a. So in this case, we have a negative b, which is a negative 2, divided by a 2 times negative 1, which is a negative 2, which means the x-coordinate occurs at a positive 1 for x. Once I get that positive 1, we'll plug that back in, and I will solve for y. So I got a negative 1 plus 2 plus 3, which is going to give me a value of 4. That means this point right here, this maximum point, that's at the point 1, 4. That's the vertex, which means the max is y equals 4. Last question they're asking here is, what's the domain and range of your function? Well, for domain, for any single parabola you draw, real easy, domain's going to be all real numbers. You can write all real numbers like this, or you can say it's from negative infinity to positive infinity. The range is the y values that are covered. And the range will be one of two answers. It'll be from negative infinity to the max, or it'll be from the min to positive infinity. In this case, since my graph is opening down, my range is going to start at negative infinity, and it's going to go until it reaches this max value, which we just determined was at 4. Now, it is allowed to be 4, which means 4 is included in my answer in this. Again, domain, always all real numbers for every quadratic. The range, negative infinity to 4, including 4. Let me give you an overall way to remember that here. So if this is my parabola, and this is the point x comma y, if my parabola is opening up, domain, all the real numbers, range is equal to y, including y, to positive infinity. However, if my parabola is opening down, and that's the point x comma y, domain, all real numbers again, because any value of x can be plugged into this. The range, the values that I get out, are now from negative infinity to y, not including y. So whenever you're asked for domain and range for a parabola, this is the way they should look, one of these two answers. Well, that's our lesson on graphing quadratics. Please try the self-check on Moodle for 5.1. And bring your questions tomorrow when we practice this in class. Have a great night.